All right, welcome to week 2 of the FTC Alberta CAD challenges. This week we're going to try to make something that's going to push a button, make it really simple. I feel like the thing that you see on screen right now is a bit of an overcomplicated version of it. But the hope is that we're going to go through a few tools that you'll find somewhat useful, up to and including the ability to use a revolve, modify existing parts, do some rigid and revolute joints, as well as potentially to put some joint motion constraints on, as well as limits and I'm looking for a term here. Motion links, that's the term I was looking for. In doing this, we got a few people in the chat room who are being recorded. They can ask some questions as they need to. If you guys don't mind muting your microphones while you're at it, unless you have a question, and we can go from there. I threw in the Discord group a few parts that I would recommend that everybody have uploaded here. They include some Tetrix parts, including some channel, some bars, so that we can build something similar to this at some point. Before we do that, though, I think we're going to start by going with a couple things. The first thing I want to create here is I actually want to create this bumper for our new project. This red thing here was actually meant to be a kind of comedic version of a boxing glove, something to just push a button, give us lots of space to work with. And so building it is kind of interesting, but you don't have the tools to do that quite yet because it uses a revolve command instead. So we're going to make a new version of this. I'm just going to go over to my entitled document here. Actually, I'm going to create a new design. Okay, I'm going to save this design as bumper pusher, and we're going to make that revolution. Okay, first thing we're going to do is we're going to drag in one of our Tetrix bars here. I'm going to try to grab my flat just because it'll work pretty well here. And this is simply going to be here so I have something to base the design off of. I'm going to drop it in here, and I'm just going to create a new component. Okay, the reason I brought this in, to be perfectly honest, is I want to use the same shape as the bar. So I'm going to project the bar just like we did last week when we were talking about this, and that's going to give me a brand new wonderful purple sketch. I really don't need this flat bar anymore. I'm simply going to delete it. I'm going to make it go away, and it's going to leave the sketch. Now, I really wanted it because I really just need this sketch to get started. Okay, I'm going to grab a circle, and I'm simply going to drag a sketch out to here. Okay, and I'm going to use that sketch to just start drawing my bumper. Okay, no real science to this. I'm actually just going to draw some lines out until they match, float over here to get your snap point, and then I'm just going to enclose them. Okay, trim away the stuff I don't need. Really, honestly, this is just a really rough version of this that is really rough version that I'm going to use to create my first extrusion. Okay, from here, we'll click our extrude function, click here, click here, click here. And all this is doing is just giving me something to attach to. Again, exact dimensions and everything really only matter for the Tetrix bar, just so we have something to attach to. Because really what we want to do to this is we want to attach a big bumper so that our accuracy on our programming and stuff doesn't matter as much. That's right, programmers. We can make it so that the design makes it so you are less valid in your role on your team. Now, when you revolve something, you're going to draw two things. You're going to draw a face, and then you're going to draw an axis of rotation. So in this case, we're going to draw our axis of rotation right along center here. I'm just going to snap to center and draw a line. That's going to be our axis of rotation there. And again, pick a number that makes you happy. It'll matter a lot on your actual design if you're designing for a challenge, but right now it doesn't really matter. From here, I'm now going to draw a shape. In this case, I'm actually going to draw a straight line here, and then I'm going to connect that straight line with an arc, probably a 3-point arc, back to the corner of this drawing. I'm going to make my bumper a little bit concave instead of convex, like my last one. Now remember, we got two things here. We now have a shape. Okay, we actually have a surface that we can use here, and we have an axis of rotation. Finish our sketch. Now, this is going to look super weird in just a second because instead of using the put my browser back here. Go. Instead of using the extrude command, which you're somewhat familiar with, we're actually going to use the revolve command. Now when we click it, we get this little menu here that says select and or axis. Okay, so we're going to select our actual profile here, and then we're going to select our axis here, just like we talked about. And what it's going to do is it's going to revolve that shape around that axis. This is how we get things like a light bulb shape, a bell shape, anything round can be created using this. All right. And we got some more people joining in the chat room here. Hello. Just so you guys know, you are being recorded if your microphone is on, so feel free to mute that if it's not something you're going to use, but also feel free to unmute it if you have questions while we're going here. You'll notice that when I created that, it actually said the degrees. If I really wanted to, I could actually go down to the bottom here, and I could actually, I'm going to edit my feature. If I only wanted this to be a half revolution, I could type in 180 degrees, and it'll create a half revolution around that same axis. Lucky for me, I do want 360. Also, we have the ability to join or to cut or to make a new body, just like we did with the extrude feature. So this can be used for all sorts of tools, all sorts of things. Okay, and again, just for kind of the presentation of this sake, we now have a body here. I'm going to take this body because I'm pretty much done messing with it, and I'm going to convert it to a component. That's going to let me drag it into other documents, things like that, and actually make some use of it. It's also going to let me do this. If I go to appearance, I can actually change the color of it. And this matters a bit when you're illustrating things for, let's say, your team, and if you're the team's CAD person, you want to kind of illustrate something to your team. I'm just going to grab an ABS white, just because most 3D printers can do something similar to that. Even if you're using PLA or other plastics, this is not a bad way to go for the design phase. I'm then going to right click and click edit because I actually want it to be red. I'm going to rename it. I'm going to drag my slider over, and I'm going to make it full bore red. Now what that means is that from here I can click and drag this onto my component, and I can actually color it whatever color I need. That's fantastic. I'm going to save the bumper pusher, and as you can see, it's going to show up down here. This is my other bumper attachment that I did before. Okay, same idea. You can see in the browser on the bottom here, it's same thing. I just revolved a very simple sketch around the space here. There you can see the sketch, and then got that. Now, this is what we're going to use to actually push the object. And it's just kind of one of those other pieces you can use to create 3D printed objects, plastic objects, that sort of thing. But the core of what we want to talk about today is how to actually attach existing objects together. And that uses the joint command. I'm going to jump over to a really simple untitled document to actually illustrate a couple things here. So I just created these simple plates. They're just a rectangular prism with a couple of holes in them. And what we really need out of this is just to see how we can attach things together. Now, if you go to the Assemble menu here, you notice that you actually have the ability to create a whole bunch of things. The two that we're going to work with today are joints and motion links. Okay, so I want to talk about joints for a second. Joints come in a variety of flavors, as they are, and they require a few things. Any joint requires two components being put together. We're going to use just simple joints today. We're not going to use between two faces or intersections because those get a little bit complicated. All of ours will be direct joined objects. We then have the choice of how much motion to put on them. Now, the two that we're going to talk about today are rigid and revolute. Rigid simply is going to fuse two objects together. Rigid are really good for simulating, let's say you're going to use bolts to bolt two parts together and make them nice and tight. They're not supposed to move, they're supposed to be rigid. That's a really good way of putting those together. If you go to revolute, it's going to expect the part to spin around itself. Now, these plates have been built to simulate the idea of putting a bolt through those holes and seeing how they move against each other. So we're actually going to choose revolute here. Now, it asks us to pick two components. I'm going to select my first component right here. Yeah, it's revolute. That's correct. Oh, here we go. Select. I'm going to select, I have a few choices here. I could select the actual shape on the edge of the cylinder, or I could select the cylinder itself. The difference here is if I select the shape here, it's going to try to snap to either the center point, or depending on how you've drawn your shape, it might also try to snap to the edge, such as what I'm doing right now. I'm just going to grab the cylinder here, and I'm going to go grab the cylinder here. Now, two of these pieces are going to go flying all over the page. That's pretty normal. Now you notice that one's going to start to spin around the other, and it's going to look super weird. It's asking me for an offset right now, and I'm going to offset it by 5 millimeters because right now that is the width of this particular project. You'll base it off your particular design. You'll notice when I stare through the middle that those holes have been perfectly aligned with each other, and they're lined up. So what I've got here, I got my selections, I've offset them by 5 millimeters in the Z direction, and I've given them a motion of being revolute. You can mess with these to make your actual joint work. Now when I press OK, what you're going to see is that these two parts are now actually joined together. But what it looks like is a rigid joint. They're not moving around each other like they're supposed to. But that's because right now there's nothing else constraining these objects. So what I'm going to do is I'm going to grab this component here, which is component 1, 3, and I'm going to do what's called grounding it. Right now there is nothing making them spin because there's nothing creating spinning forces on them. But if I right click on this and click ground, it's going to make it, and I'm just going to capture my position there, it's going to make it so that part can't move. It just physically doesn't go anywhere. And in doing that, it's going to give us the ability to actually create a rotational force around the other piece. This is going to let it spin. Now, there's a few other pieces you need to know here, okay? We just grounded something so it can't move. We've got the rotational axis, or rotational motion here, and the last thing we're going to do is we're going to actually play with another couple of joints here, and I'm very quickly just going to grab another part here, cylinder to cylinder, and you'll notice they try to connect them together. That's awesome. I'm going to offset it by 5 millimeters again. I'm going to press OK. Now I've got a piece that spins here. I'm going to spin my view around so you can see. This one moves here, this one moves here. Okay? If it turns out that these two objects are going to move in concert with each other, they're going to move together, I can actually go up to my Assemble button and I can actually put a motion link on them. Motion link is going to do something really simple. If you can see down here, this shows that I've got my axis, my current axis here, and my current axis here for these two parts. And they actually show a distance. This one's -105, and this one's at 175. Okay? If I want them to move together and start at the same point, before I do this, I might want to just change that by double-clicking on it, and I might just want to change it to, I'm going to change it to 175. Okay, so clearly this one's 175 and the other one's 175 are not the same, which means we started them at a different point. And I'm going to go down to, I believe it's going to be 85. Nope, it's going to be -85. Oh, I was so close. Okay, once we've got them matching, regardless, we're going to make the motion link. What this is going to do right now, if I grab this one, it moves. Grab this one, it moves. A motion link is simply going to make it so that this rotational joint and this rotational joint are going to move together in concert with one another. We can choose what angle we want them to move at. In cases of like gears and pulleys, this is actually useful because, like, let's say we want one side to spin faster than the other side, we can actually accomplish that here. It's literally, when we talk about gearboxes, how we're going to do it. And yes, sometimes things get weird. Let's press OK. What this is going to do is that as one of these moves, the other one is also going to move, which is kind of useful if we're talking about something like the lift that we were trying to build in the original model. I'm going to click undo twice. Actually, I'm even better. I'm going to go up into my joints folder in my browser, and you'll notice that I have a Revolute joint here that highlights this one. I have a Revolute joint here that highlights this one, and I have a motion link right here. Okay, I'm actually going to delete my motion link. I'm just going to make it go away because there's another way of accomplishing what we need to accomplish, and that is to put 2 more joints on this thing. Hello, Martin. Welcome. Just so you know, you are being recorded. If you don't mind muting your mic. If you have any questions, unmute yourself. Feel free to ask the question, and we'll go from there. We're just partway into putting some joints on this particular drawing right now. And yeah, I'm just going to offset this by 5 millimeters again, just so we get that right. And then I'm going to take this piece here, and you'll notice that this actually does some really weird and wacky movements now once we've detached that. And we're going to attach it back onto the other side. Now, for those of you playing along at home, you might realize that this particular setup right here is going to, if I set it up just right, is going to create a really interesting puzzle. Because now that I've connected all 4 of those pieces, and I know that this bottom piece here is grounded, that means that if I move this, categorically the other pieces of this drawing have to move with it. So we've in essence created that same motion link by just attaching things together. We don't necessarily have to put that motion link into place. The last thing you can do, because you'll notice that this is kind of weird, if I go past my space here, or past my edge, it actually just makes the pieces fold over each other. Okay, I can actually put limits on this, and I'm going to do that right now. And I'm going to just put it right here where it would make contact. I'm going to note that my angle right now is 120 degrees, and I'm going to click on this joint. Okay, I'm going to right click, and I'm actually going to edit the joint limits. Okay, I'm going to put a minimum and a maximum on this one because its minimum is going to be negative 120 degrees, which is where it just was. Okay, its maximum right now, I can leave it at whatever I want to for right now. Ooh, that created some fun stuff. I'm going to go back and redo that just because clearly the minimum limit did some weird stuff. Edit joint limits. I'm going to put the minimum at negative 120 degrees. I'm going to uncheck the maximum for now. Oh, I need a maximum. Maximum is going to be, if that's negative 120, that means I'm going to have a maximum that's probably about, I'm going to say negative 180, and we're going to try that out. Okay, Press OK. Now we've created a place where this piece is now completely stuck because I put the limits in the wrong spot. Apologies, guys. That happens sometimes. Minimum, maximum. Here we go. Let's try this again. -120. I'm going to change this up to 170. That's going to put it there. And we're going to go try to move this. Okay. Clearly I put my limits on the wrong side. Okay. Back to this we go. Edit joint limits. Had them backwards. -120. 170. It's going to be a little further than that, isn't it? 180. Let's go 210. What you're seeing right now is that the angle is actually going a little bit further or not as far, okay? And it's going to actually limit this. We're going to do this in our actual drawing here, and it's going to look a little bit more noteworthy. So again, for those that just joined us, our goal is to try to build something similar to this using existing parts. But there's one more thing we need to do to accomplish this. So you'll notice that all of these parts that are here, except for this red thing, which we just created over here as a bumper pusher of some sort, or our version of it, all of these things exist as Tetrix parts. You could use Rev parts as well. They work equally well. We could create this. We kind of have all of the things we would need to create a mechanism like this based on what I showed you. But I want to show you one more thing because there's a couple things of note that you might have seen on this one. We created this red piece brand new from scratch. This bar is stock, this bar is stock, the brass bushings, the axles, everything else is pretty much stock. It comes out of the kit of parts. But there's something weird you might notice. Everyone see these bars right here? They're a bit funky. If we make this bolt go away on the end here, you'll notice that the hole on the end is actually bigger than the holes in the inside. Now we do this all the time for robots because we need to modify parts. We want to put a 1/4-inch bolt through a hole that was never meant for a 1/4-inch bolt. That's pretty normal. So we're going to talk lastly, before I leave you to do some of this, around how to actually modify a part. So we're actually going to get that part, which was the Tetrix Max 288mm flat bar. I'm going to double click on this and it's going to come up in my browser. Now, the first thing I want to do if I'm making custom parts is I want to actually create a new part file. And the easiest way to do that is to go up to my file menu and to go save as. Once I go save as, I can actually change the name of this. So I know that I'm going to make this half as long and I'm going to actually name it as such. I'm going to name it 144mm flat bar and I'm going to name it custom. Just because, just to show that I'm going to customize some other things on it. You can describe things as you want. They should be put in here in a way that can be recognized, that your team can find out kind of what they're looking at. So now, first thing, I see this bar. I know that it's 244mm across. There's a couple of ways that I could make this happen. Both of them involve sketching something on here. So we're going to start one way by just drawing on the end of this. Now in our last tutorial we talked about the idea that you could actually use this project tab to project other pieces of this drawing. We're going to do that. What that's going to give us is an actual sketch on the end of this drawing that is the exact same size as the bar. That's important. When we finish the sketch, we can now take the extrusion button, click on all three of these, and we can actually pull these back. And you can see it's actually deleting the part as it goes because it's automatically figured out that, hey, I can't join anything into an existing object, but I can cut. So it's actually using cut. In this case, we are going to use cut, and we know that it's going to be negative 144mm because that's exactly what we wanted to cut off of this thing. Press OK. Now our bar has been modified downwards, okay? I've got a little bit of a fillet on the end. I'm just going to add a fillet on using the fillet tool. I'm just going to fillet this off by about 1 millimeter. There we go, 1 millimeter, 1 millimeter. Okay, cool. So now we've got a modified bar. It's definitely a different size. It's much more akin to this size bar than the size it was before. From here now, we're simply going to turn around and extend the holes out. Doing that's relatively easy. Click Create Sketch, choose a side of your object, and we are going to put a hole here. I was basing it on 1/4-20 bolts, which if memory serves are, I'm just going to grab a quick calculation here, 6.35 millimeters across. Again, 6.35 millimeters across, and I'm going to do the same thing on the other side because why not? Actually, the other side's going to be 6 millimeters across because it's going to take a Tetrix axle. I finished my sketch, and now this gives me the place where I can actually extrude out the outside of this. Now, if I go beyond where I'm supposed to on here, if I go too far, there's nothing really wrong with that. It really doesn't matter. I can actually select another profile here. They'll both go out 13. They'll cut that out, no problem, okay? If you prefer more accuracy, you can get as close as you need to actually make that cut. Those being there, we can now go ahead and save this part, and you'll notice that in my actual design, all my part catalog here, I actually now have a new part here. It's sitting right next to the 288 millimeter flat bar. It is a 144 flat bar. This one I put custom on just so it'd be named something different than the one that's already in my design. Now, with all of those tools, putting this together is actually relatively easy. So I'm gonna I want to talk to you about one thing very briefly, and then I'm gonna put together the basic mechanism one more time using some of those revolve constraints just to show you how this works with a real Rev project. Now, for your challenge, I just want to point something out. Your challenge does not say you need to use this kind of mechanism. Your challenge doesn't say this is how you need to solve the problem. This is just one way of solving it. There are other ways of solving it. You could simulate a rack and pinion gear if you wanted to using the same motion constraints. Okay, there are dozens of different ways, but there's one thing I'm going to ask everybody here to not do, and it's what we often call in robotics the cantilever of death. And I'm going to show it to you right now. I'm just going to make my one work plane I have here go away. Perhaps not. Oh, there we go. When did I put the work plane in? Okay, I want to, okay, I guess the plane is there to stay for now. Okay, so if you look at this, there's something very noteworthy. A lot of students I see in robotics do something that I don't necessarily agree with. They'll actually go in and take their servo, their standard servo itself, and what they will do, clearly this one imported upside down, such as life, and what they will do is they will actually attach their mechanism directly to the servo horn. And yes, that's the terminology, this is your servo horn, okay? That servo horn is not very well supported because if we make it go away, and I'm just going to open up my bodies here, this drawing, this particular CAD model has two bodies in it. It has the servo and it has the servo horn. I'm going to make the servo horn go invisible. You guys may have noticed that I actually have another drawing over here, which is the standard servo where I've just deleted the horn. Okay, I also turned it blue using that appearance tab so I could see it, but I want to show you something. This is the end of a servo. And the end of the servo, if you're lucky, is made out of a bunch of brass, a bunch of gears on there that are actually going to help you attach things to. They are not very strong. Right? Servos by nature are not the strongest component on your robot, and I wouldn't treat them that way. This is prone if you put your subsystems directly on the horn at the end of your servo, you're prone to breaking it. You're prone to bending it. It doesn't like those kind of lateral torsion forces on it that are going to bend things off of it, and that's often where we find servos that get completely butchered in robotics competition. So it's really a good idea when you're building it to actually go out, and I have lost my bumper system here. I have too many things open clearly. There we go. Okay. It is actually a really good idea for you to do what I've done here. Now I've taken the servo and I've attached the adapter to it, which Tetrix sells. It's part of their servo kit. And then I've actually just simply placed this on the edge of the channel. The reason for this is that if anything is going to apply force to our main subsystem here, our main arm, the force and lateral force specifically, so anything that is, in a shear direction, it's kind of moving up or down here, is going to actually apply the force to this brass bushing. It's not going to affect the servo as much. This protects your servo from damage because you're not putting the force directly on the shaft of the servo. If, worst case scenario, if I have to replace the servo, it's relatively easy. I don't have to replace the whole thing, but it's less likely to be damaged because I've actually put it in here. In an ideal world, my CAD just didn't quite work out the right way here, I would actually put a brass bushing on both sides so that I have an actual axle that's supported on the main tubing on both sides. That would be ideal. This prevents you having snap servo axles, snap brackets, things like that. All right. Now that being said, if we want to build one of these, I'm just going to put a very simple version of this together with no servo, just so we can re-illustrate a couple of those terms, or a couple of those concepts, and then we can absolutely go from there. You'll notice I've also put the actual shaft bearings on here, so that you can actually adapt these to the D-shaped shaft of the Tetrix kit. I'm going to omit a few pieces here just for the sake of simplicity. Alright, so what we're going to do is we're going to start up a new design. Okay, we're going to save it as button presser. And then we are going to build the thing. Okay, very simply, we're going to drag in a short channel. Sweet, and I'm going to give it a little bit of a spin so that we can access the bottom of it, because then you have some way of bolting it down to your chassis, which is relatively easy. We're going to grab our custom bars here. And grab one, and I will copy it over. Okay, and I'm going to spin it around so that it is vertical 90 degrees, and I am going to probably leave it right there. I'm going to do a little inspect function just to find out which hole is which. Okay, this hole is my 6.35, so it actually is supposed to go at the top. So let's grab our flat bar, and let's give it a spin. There we go. Awesome. Now, I'm going to end up having two of these in here, and I'm also going to end up having one more flat bar that's going to bring this all together. And that we're going to attach here. Apologies, phone call coming in. There we go. Let's join this thing into place. So first of all, capture position. I'm going to capture this to right here. I'm going to capture this to right here. And you're going to see some weird spinning going on here. That's fine. Okay, now, the last thing I typed in was a revolute joint, so it is going to do a revolution, okay? I'm going to select these things. I don't need to offset this because of the places I chose, and again, when I move this, nothing happens. That's because I have not grounded my channel. Let's ground our channel, and then we see that once we ground that, we do get the rotation that we want. Life is good. Let's take this piece, let's copy it and paste it, and in copying and pasting it, I'm able to bring another one back into place. Life is good, life is good, press OK. Let's attach this thing into place. I'm going to use the flat side here, and I'm going to choose to attach it over here. Now you'll notice right now that I'm actually attaching things, though in reality I'd probably have brass bushings, I'd have bolts, things like that. It's not a bad idea to build the basic mechanisms this way before you get to kind of those more minutiae things. I can prove at a high level that this design is going to work before I put the bolts into it. That's really powerful because I might be able to modify the design and design around something or potential problems if I need to beforehand. I'm going to drag my flat bar in here. I'm going to give it a little bit of a twist, 90 degrees, press OK, and then I'm going to drop our new bumper pusher in. There's some questions coming in. Yeah, fire away, man.
Would you put a limit on those two bars to
yeah.
The two bars on moving?
Yeah, we absolutely could, and I think I'll illustrate that in just a second here. So I'm just gonna quickly, I've thrown this bar in. I'm just gonna this pusher piece here. I'm actually just going to attach it, but I'm not going to attach it with a rotational constraint. I'm going to do a rigid constraint. Excuse me. That means that this bar is going to move all as one unit, which is kind of what I was looking for. Now, one thing I want to note, if you're attaching things that are going to have constraints in them, one problem you may run into, and I'm going to show it to you just so you kind of can recognize it, because it's something that I've fought a fair bit with on this particular design. I'm just going to select the end here. That's all good. I don't want that to be rigid. I want that to be revolute. So we're going to do a revolution. And again, we get some really weird motion out of this thing. That's pretty normal. Now, I know because these bars are the exact same size that when I create this particular design, I can attach them all over the place here and put those revolutions on here. But in a lot of cases, so I know that I've got 1, 2, 3, 4, 5, 6, 7, 8. We're on the 9th major hole here. 3, 4, 5, 6, 7, 8, 9. So I'm going to attach this here. But let's say I decided I missed and I attach here, okay? What's going to happen to this? This should try to revolve around here, okay? When I press OK, what I'm going to end up with is, oh, wow, okay. That actually worked. I didn't think that one was going to work. Hey, so be it. Okay, depending on where I attach them, I'm going to get a really weird angle on this. And in some challenges, that might actually be useful. However, I don't want it. Going back to my joints, I'm just going to delete that revolution completely, and now we're going to try this again, okay? I'm actually going to attach this where it's supposed to, which is going to be here to right here. Again, nice rotational joint. There we go. Now I should get parallel motion. And so, Tristan, to answer your question, let's go to this last piece here. So I know that at this point right here, this is realistically going to be our limit, okay? And I'm just going to grab this joint right here, and I can see right now that it is set to negative 75 degrees, okay? I'm going to go with that as my measurement. Okay, I'm going to take it, I'm going to right-click it, and I actually have the ability to edit the joint limits. So I'm going to go negative, I'm going to do the same thing I did before. Okay, I'm going to set this as its minimum. I said negative 75, okay? And I'm going to go with a maximum of, I think, 180 degrees right now. Okay? Now, what's that's going to do is when I hit that negative 75, it's going to stop right here. Okay. Now we also know that there's going to be another limit on this, which is going to realistically happen right about here. Okay. Again, depending on your servo, but this is about the point that these bars actually start to run into one another, where they just physically can't go any further. Again, you'll probably have some hardware in the way that will prevent this in this particular design, but for the sake of this tutorial, let's take a look here, and let's go back to our angle. We now know that it's 82, so let's go back to this. Let's edit our joint limits, and we'll just change this to 82 degrees. Okay, press OK. And now what that should create is a joint whereby both sides are limited based off of the natural constraints of the particular hardware, and that I can test this entire subsystem to see if it's going to function. This is going to let me actually design better parts for my robot, because I can go in here and see, yep, this is going to be able to extend out, and let's say I'm mounting this on the edge of my frame, and I could even go as far as measuring this if I had to, right? I can know from the edge of this to the edge of this, I'm probably going to exceed my frame perimeter by 300 millimeters. That's awesome. That might help me solve a particular design challenge for a particular problem. Now, is it probably overkill for the velocity vortex example that we threw out there? Yes, it probably is. But it illustrates some things that you guys should know about designing moving subsystems for an FTC robot. So that's pretty much everything I wanted to go through. So if you guys have any questions here in the group here, fire away, and if not, we'll call that a demo, and you guys can go design some subsystems to actually try to make this work.
You would do this with a rack and pinion as well, correct?
You would. And what you would do is you would actually put that revolute joint, so that rotational joint, on the pinion gear. You would then actually put a linear joint on the other gear. So give me a second here. I'm going to hop in and I'll show you the motion. You do have the ability to build a slider joint, and if that is what you're going to do, a rack and pinion, clicking the slider, it's pretty self-explanatory. It's somewhat like a revolute. It will move from one side to the other. It will have a minimum and a maximum movement. It makes a lot of sense. All you would do is you would take a slider joint, and you would take a revolute joint, and then you would motion link the slider joint to the revolute joint, or vice versa. That way, when the pinion gear moves, the rack gear will move in concert with it. Does that make sense?
Okay.
So instead of motion linking two revolutes together, you're just motion linking a revolute to a slider.
Okay.
Yeah.
And for that, you would probably use a continuous rotation servo, correct?
That is correct. And in the case of this design, the casing on a continuous rotation and the standard servo are identical, so we can just make those. We can make those go from here. There's nothing wrong with those at the design phase. I would just put a note somewhere in your design. This should be continuous rotation.
All right, team.
Cool. Well, if there's no more
Thank you,
questions,
Mitch.
guys, I hope you enjoyed that. And yeah, enjoy your CADing. Any questions on the Discord, fire away, and life is good.
Thank you, mate.
Thanks, guys.